Here's another example of a problem where we're adding two vectors together to find the resultant vector c. So let's go about doing this problem. The first thing we do is we look at what we're given. So I've written over here what we're given. So what we know, starting with this problem, is the two magnitudes of the vectors that we're adding together. And I put units on it just because usually these problems have units. We also know the angle of A with respect to x, the x-axis, and we know the x component of B. So we're going to use what we know here to solve for the magnitude and the direction of this resultant vector c. So, as usual, let's start with one vector at a time. So let's start with A. What can we do with A? Well, we know the magnitude and we know its direction, and we need to solve for the components here so that we can solve for the components of C. So, what can we use to solve for components? Well, we want to solve for the y component and the x component of this triangle, so we can use either sine or cos to solve for one of the sides. So let's first solve for, let's use this equation, our cosine trig function, and let's solve for the x component. So multiplying over, this would be, that's multiplied. So we get this, and now we can plug in our numbers. Our magnitude of A is 4 meters times cosine of this angle, and that ends up working out to, sorry, this is 3. That ends up working out to 2 meters. So there's our x component of A. Now to solve for the y component of A, there's two things we could do. We could either use Pythagorean's theorem, because we know both the magnitude and this component, or we could just use our sine function. So let me do that. I'm going to do the sine function, which is the y component over the magnitude. And similarly to what we just did here, ay equals a magnitude of A sine theta. So 4 meters times sine of pi over 3. And that means AY is, if you put it in your calculator, 3.46 meters. Okay, now we can move on to B. So B, we know BX already, so let's write that out. That's 2 meters. Now we don't know an angle, so we can't use any of these trig functions, but we do know the magnitude. So what we can do is use Pythagorean's theorem to solve for the y component. So that would be by is equal to the magnitude of b squared minus the magnitude of bx squared, all square rooted. Plugging in numbers, that's 3 squared, 3 meters squared, minus 2 meters squared, and this by works out to 2.24 meters. Okay, now we have all the components of our initial vectors, our two vectors we're adding together, which means now we can find the resultant components, or the components of C. And we can just add the x component of A with the x component of B, and the y component of A with the y component of B. So Cx is 2 meters plus Bx, which is also 2 meters. So Cx is 4 meters. Cy, that would be AY, 3.46 meters, plus BY, 2.24 meters. And so our y component of C comes out to 5.7 meters. Okay, now we can find the magnitude of C using Pythagorean's theorem. So 4 meters squared plus 5.7 meters squared, all under the root. And this comes out to, if you round it up, we'll say 7 meters. Okay, so we have our magnitude of our vector now, 7 meters. Now, last thing to do is find the direction. So, to find that, let's take, we know our x component, we know our y component, and we know our magnitude, but we can use these components with our tangent function to solve for the angle. So cy over cx, which the angle we're solving for now is this one here, if you can see that, the one from the dotted line to the x-axis. If we use our inverse tangent function, arctangent, cy over cx, that is arctangent of 5.7 meters divided by 4 meters, which works out to rounded 55 meters. And finally, as always, our last step is to write out the vector in its proper form. So C is equal to 7 meters at 55 degrees. Now it's with respect to the x-axis, the angle, in the first quadrant. So it's 55 degrees north of east. So that's how you do that problem. Thanks for watching.